Right, so we'll do an example to illustrate the techniques we learned so far on how we can find the bandwidth of an amplifier. We're given this A of S gain function, and we want to find omega h for such an A of S. This is the form that we saw previously. A of S is a m times a product of the form 1 plus s over omega z1 into other factors and divided by 1 plus s over omega p1, and we have a p2 here, and possibly other factors. This is the form that we have, and we can tell that am in this case is equal to 1. And also that omega z1 is minus 10 to the 5 radians per second, and that omega p1 and omega p2 are 10 to the 4 and 4 times 10 to the 4, also in radians per second. So these are the zeros and the poles for this gain function, and we want to find omega h. If we are given the function and we can determine the location of the poles and the zeros, we always try to answer the question, is there a dominant pole? And if there is, then this would be the value, an approximate value for omega h. So we sort the poles and the zeros in absolute value. What do I have? I have 4 times 10 to the 4. Before that, I have 10 to the 4. And after that, in absolute value, I have 10 to the 5. And there is this 0 at infinity that we will not show. So this is the order, omega p1, omega p2, omega z. The ratio between the first two critical frequencies is exactly 4. And this is the minimum required to declare that the smallest pole is dominant. So I can do that because here omega p1 meets this condition. I can say that an approximation for this bandwidth, omega h, would be just the value of omega p1. Omega h is approximately 10 to the 4 radians per second. So this is a quick way to find omega h. If I want a better approximation, I can use the square root of the squares or the square root of the inverse of the squares formula, which gives me omega h in terms of all the critical frequencies. Omega h is approximately 1 over the square root of 1 over omega p1 squared plus 1 over omega p2 squared minus 2 times 1 over omega z1 squared. Omega z2 disappears. And if I do this calculation on my calculator, then I get 9,800 instead of 10,000. So pretty close to omega p1. Omega p1 is the dominant one. If I want to compare with the exact value, I can use the definition at the exact value of omega h, the 3 dB frequency. A, the magnitude of A would be the magnitude of A at low frequency divided by root 2. And from that, I can develop a polynomial equation that will give me the value of omega h squared. And the polynomial equation would be of this form. 1 plus x over omega p1 squared into 1 plus x over omega p2 squared equals 2 times 1 plus x over omega z1 squared. If I have other poles and zeros, then they would appear as factors here, and the polynomial would be of a higher degree. But this one here is quite simple. This is just second degree, and I need to solve a quadratic equation to find x. I know omega p1, omega p2, and omega z1, these are just numbers. So this is simply a quadratic equation. So solving for x using the quadratic equation formula, I find x, but x is not omega h, x is omega h squared. So omega h would be the square root of x, and this is the numerical value that we get, 9,573 radians per second. So the dominant pole approximation gives me 10,000. This is almost 9.6 thousand, and the approximation in the middle is 9.8 thousand. So all the answers are pretty close to each other. And if I want to just find the value of the bandwidth very, very quickly, then I'll just stop at the dominant pole and say, well, that's almost 10,000. And the exact is probably few percent away from that. The error is just few percent, 4 or 5%. Let's do the magnitude Bode plot for such an A of S. So this is our A of S, same example. Let's do the Bode plot for that. And for now, I will show the Bode plot without explaining how we got it. The blue curve is the exact one, and we can get it from maybe a software tool like MATLAB, or PSpice can do it, or other similar programs. So we can do the Bode plot, the exact one, the blue curve. And we will learn next how we can construct the approximate one, the black straight lines. So this is what we have, and you can see here's 10 to the 4. So this is the approximation for the bandwidth, and this is the exact one. So on the left, 9,537, and on the right, 10,000. Omega is in radians per second, and the x-axis is log scale, and on the y-axis, I have 20 log A, and notice that the maximum here is 0, because AM is 1. So in dB, this is 0 dB. 1 is 0 dB. So the maximum here is 0 dB, and then it starts to drop with an omega h value, a 3 dB frequency of around 9.6 kiloradians per second. So this is how it looks like. Now let's see how we can construct this. If I have more than one pole, or more than one zero, and or more than one zero, how can I construct the Bode plot? How can I get the black approximate plot? And there's a very nice, simple way to do that. So let's look at this procedure. We sort the poles and the zeros in absolute value and show their locations on the omega axis. We start with the dB value, which is A of 0, so 20 log A of 0. And if there is an S term, which we did not show, just in case there is an S term, then there will be a starting slope. But we will rarely see that. And then we move along the omega axis. So we're now walking along the x-axis. If we encounter a pole, if we meet a certain frequency, which is a pole frequency, the slope of the Bode plot after the pole would be the slope before the pole minus 20 dB per decade. If we encounter a 0, and that can be an absolute value, then the slope after the 0 would be the slope before the 0 plus 20 dB per decade. So a pole would make me lose 20 dB per decade in slope. A 0 would make me gain 20 dB per decade in slope. This is a simple procedure. Just mark the critical frequencies and adjust the slope when you see one. There is also a procedure for phase, and this one is slightly more, I wouldn't say complicated, but has variations. And you can review this later if you want to see how you can also construct the Bode plot for phase if you have the critical frequencies. It's a very systematic procedure. You can follow it. You can implement this as a computer program, and the computer can do the Bode plot for you. So let's apply the procedure for the magnitude Bode plot. We'll apply it to the example that we have. We said that we need to mark the pole and zero frequencies. So I have 10 to the 4, which is here, and that's a pole, it's a P. I have 4 times 10 to the 4, and this is here, and it's a P, it's a pole. And I have 10 to the 5, absolute value of minus 10 to the 5 is 10 to the 5, and it's a 0, and I mark it with a Z. So I have P at 10 to the 4, P at 4 times 10 to the 4, and Z at 10 to the 5. And the original value, I start with 0 dB, because this is the low frequency gain is 1, and that's 0 dB. So I start there. And then we're moving along the omega axis now. So we're walking along the omega axis in this direction. So we continue, as long as we don't see a pole or a 0, nothing happens. And we continue with the level 0 dB. And then we reach 10 to the 4. And what is this? This is a pole. The procedure states that if you encounter a pole, right after the pole, the slope would be the slope right before the pole minus 20 dB per decade. So the slope after 10 to the 4 would be the slope before 10 to the 4. It was 0. It was a horizontal level, minus 20 dB per decade. This is what the procedure tells me. So what is the slope here? Well, it was 0 dB per decade. Now it's minus 20 dB per decade. All right, so that's easy. We continue our walk along the omega axis, and now the Bode plot is a straight line with a minus 20 dB per decade slope. The next critical frequency that we encounter, that we meet, would be also a pole, because this is the first one, P1, P2, and 0. So after this one, after the second pole, the slope would be whatever the slope was before P2 minus 20 dB per decade. Before P2, the slope was minus 20. And because of P2, I will lose another 20. So the new slope would become minus 20, minus 20. So this is minus 40. So the slope here would be minus 40 now, dB per decade. And the slope here was minus 20 dB per decade. And the slope here is 0. This is horizontal, dB per decade. All right. Now for an interesting question. What is the value here? What is this value in dB? I can read from the plot that this is minus 12. But how can I calculate this? I want you to think about it and come up with the formula that gives this. How is the value at this point? Why is it equal to minus 12? So I'll give you some time to think about it and type your answers in the chat window. Okay, so the first way to solve this is to notice that I have exactly 2 octaves between 10 to the 4 and 4 times 10 to the 4. So this is the first octave, a doubling of frequency, and this is the second octave, octave 1, octave 2. And minus 20 dB per decade is minus 6 dB per octave. So if I lose 6 dB per octave and I have 2 octaves, then this is the 6 dB I lose for the first octave I reach here, and this is the second 6 dB I lose to reach the last frequency at 4 times 10 to the 4. So this is the second octave, and therefore This is the minus 12 value because I drop 6 and 6 because the distance here is exactly 2 octaves. So that's one way to explain why this is minus 12. But what if this is not a multiple of octaves or a multiple of decade? What if it's not a complete decade or a multiple of decades, or a complete octave or a multiple of octaves? Is there a general formula that we can use to find the gain at a certain point along the asymptotic Bode plot? If I have the slope, well, let's see. What is the number of decades going from omega 1 to omega 2, from a certain frequency omega 1 that is smaller than another frequency omega 2? The number of decades going from omega 1 to omega 2 is log base 10 omega 2 over omega 1. So for example, if omega 1 is 1 and omega 2 is 10, if you apply this formula, you get log base 10 of 10, and that's 1, and that's exactly 1 decade. So yes, if I take omega 1 equal 1, omega 2 100, then this is 1 to 100 is 2 decades. And if I take the log base 10 of 100 over 1, I get also 2 decades. So this is the number of decades that I get if I go from omega 1 to omega 2. So if I go from, let's say, P1 to P2, which is P1 is 10 to the 4, and P2 is 4 times 10 to the 4. How many decades is that? This is log base 10 of 4 divided by 4, 10 times 10 to the 4 divided by 10 to the 4. So this is log base 10 of just 4. So if I use my calculator to find the log of 4, I get 0.6. So this is between the distance between P1 and P2. This is 0.602 decade. So it's not a complete decade, it's not a multiple of a decade, it's a fraction of a decade. So if I go from P1 to P2, these 2 octaves, this is 0.6 of a decade. This distance is 0.6 of a decade. It's less than a factor of 10. A factor of 10 would have been 1 decade. This is a factor of 4. A factor of 4 is 0.6 of a decade. So if you take this 0.6 and you multiply by the minus 20, so I lose minus 20 dB for a decade. How much would I lose for 0.6 of a decade? This would be this drop. This drop would be minus 20 times 0.6, and it's exactly equal to the minus 12 here. So minus 20 dB per decade times the distance in decade, and that's 0.6 decade, fraction of a decade. I get the minus 12 also. So this is a general formula that you can use to estimate how many decades you have between 2 frequencies. And if the gain at omega 1 is G1 in dB, and the slope between the 2 frequencies is small a in dB per decade, then here's another formula for the gain at omega 2, also in dB. It will be G1 plus a times log base 10 of omega 2 over omega 1. So in the previous calculation, G1 was 0. We were still at the low frequency gain, 0 dB. The slope was minus 20, and the 2 frequencies were 4 times 10 to the 4 and 10 to the 4. And if you plug in these numbers in your calculator, you get the gain at the point we were after, and you get minus 12 dB. So this is how we can explain the minus 12 dB. So now that we know this, let's explain this point when we reach the 0, and explain the slope after this point. The slope after this point is the slope after we encounter a 0. And the procedure tells us that if you encounter a zero, then the slope after the zero would be the slope before the zero plus 20 dB per decade. So here before the zero, the slope was minus 40 dB per decade. And right after the zero, I get minus 40 plus 20, and I'm back at minus 20 dB per decade. All right, so this after the zero has the same slope. This line after the zero has the same slope as the line between omega p1 and omega p2, while this line has minus 40 dB per decade slope. What about this? What is this value in dB? Well, now I know how I can find this. I have a line between this frequency and this frequency. So here, 4 times 10 to the 4 and 10 to the 5. And the slope is minus 40. I can apply the formula, which states that the gain here, which looks like minus 28, seems to be minus 28. But I can use the formula that the gain at this point, corresponding to the zero, would be the gain at this point, corresponding to P2. So G1 is minus 12, plus A is the slope. The slope between these 2 points is minus 40 dB per decade, times the log base 10 of the ratio of the last frequency, the final, divided by the initial. So 10 to the 5 divided by 4 times 10 to the 4. And this, let me see how much would I get if I use my calculator to calculate 10 to the 5 divided by 4 times 10 to the 4. So 2.5 log base 10 of that is 0.4 times 40 with a minus sign, and then minus 12. And I get 27.92. So this is not exactly minus 28. This is 27 minus 27.92 dB. So this is the gain at this point as calculated from this formula. But remember that this formula is giving me the gain for the asymptotic plot, and that the actual plot, what was the blue curve, is not exactly following the black lines. There are no sharp corners in the blue line, but this is a very good approximation to the blue line. And this is it. This is the Bode plot for magnitude, or the asymptotic approximate Bode plot for magnitude. If I want to approximate the actual Bode plot, I would do something like this. So it will be a curve that goes through here, maybe. This will be the approximate Bode plot, the blue curve that we had previously. Right, so the techniques that we learned 3 techniques so far. The first one was the dominant pole approximation. The second one is the square root formula, and the third one was the exact. Solution from the definition of 3 dB frequency. All of these, and also the Bode plot construction, all of these assume that we are given the transfer function. So we start from a transfer function, and if we are given a transfer function like the one we see here, we can now find the bandwidth, construct the Bode plot, solve the equation exactly. We have now a nice set of tools if we know the transfer function. So someone should tell us this is the transfer function. If we're given the transfer function, we're good now. But what if we're not given the transfer function? What if we're given A circuit, a common source amplifier or common emitter amplifier, two very popular amplifier configurations. How can I find the bandwidth of the common source amplifier or the common emitter amplifier? A circuit like this. So I don't have now the transfer function, I have the circuit, and I want to find the bandwidth of such an amplifier. Maybe we can find the transfer function now and then use the techniques that we know. So we'll have to do an additional step, which is find the transfer function first, and then from the transfer function, find the critical frequencies, the bandwidth of whatever it is that you want to find. So this is reasonable, makes sense, since we know the steps after finding the transfer function, and now I have a circuit, maybe we can find its transfer function and continue with the stuff that we know. So here's a circuit, the common source amplifier, and we want to find now its transfer function. What is VO over Vsig or VO over Vi? And here's the same circuit with the capacitors that we talked about that are inside the MOSFET, that come with the MOSFET. So for Q1, you see the three capacitors for Q1, CGS1 between gate and source, CGD1 between gate and drain, and CDB1 between drain and source. And it appears between drain and source because B is internally shorted to S. So these are the capacitors for Q1. So this transistor comes with three capacitors, and we're showing them here to emphasize that we now have capacitors in the circuit. And if I want to find the transfer function, I need to consider these capacitors, and they become impedances. Each one is 1 over SC, and this is how S enters in the transfer and the gain equation, and it becomes a transfer function of S. For Q2, I also have CGS2. This is the source of Q2. This is the gate of Q2. CGD2, this is the drain of Q2. And CDB2, and again, the body and the source for Q2 are shorted together. Okay, so now I have this circuit with 6 capacitors. That looks a bit complicated. Let's see if we can simplify it. In signal analysis, the supply becomes like ground. So in signal analysis, the supply here is signal ground. So that's interesting because this here, I had also a DC voltage here that also is signal ground. This V bias becomes signal ground, and VDD becomes signal ground. And now this capacitor is between ground and ground, and I can neglect it. I can remove it. A capacitor connected between ground and ground won't do much really. If you look at CGD2, this one, it's between this is the output node, and signal ground. So I will color it as green, because this CDB2 is also between the output and signal ground. So I will also color it green. But also CDB1 is between the output, which is this node, and ground. So the 3 green capacitors are actually in parallel when we're doing signal analysis. CGD2, CDB2, and CDB1, they're all in parallel. And what I can do is I can replace them. Instead of showing 3 capacitors, I can show just 1 capacitor. So a C green would be CGD2 plus CDB2 plus CDB1. So now I have this instead of the 3 green capacitors. And then I have the blue capacitor, which is not really in parallel with anything. So it stays. And CGD1 also stays. It's between the gate and the drain of Q1. All right, so it's really not 6 capacitors, more like 3 capacitors. CGS1, the input is here, VI is here. CGS1 would appear between the input and ground. The blue, the green, this is C green, would appear between the output and ground instead of the 3 that we have here. And this one, CGD1, would appear between VI and VO, between the input and the output. So I have 1 capacitor between the input and ground, 1 capacitor between the output and ground, and 1 capacitor between the input and the output. So here's the small signal equivalent circuit after doing the capacitor combination. CGS1, we said, appears between the input, between gate 1. This is G1, the gate of Q1. This is VI here. The voltage at this node is VI. V-sig, R-sig, CGS1. Okay. And then CGD1 appears between the input and the output. So at the drain here, the voltage at this node is the output. And then GM1, VGS1, RO1. And then we have RO2. What is RO2? RO2 is the small signal equivalent of Q2. This is a previous result that we know. And C green from the output to ground. That's the small signal equivalent, showing everything we know about low frequency models like RSig, GMVGS, RO1, RO2, and the additional stuff about the capacitors, CGS1 between the input and ground at the gate of Q1, CGD1 between the input and the output between the gate and the drain of Q1, and C green, the sum of the 3 capacitors. And it's the sum of the 3 capacitors because they're in parallel between the output node and ground. The 3 of them are in parallel because they're connected between the output and ground, and therefore the equivalent capacitance would be the sum of the 3. So C green is the sum of the 3 green capacitors on the previous slide. I can also combine RO1 and RO2 and call this combination R prime L, and it may include also if there is an RL. So R prime L is RO1 parallel RO2, and if there is an RL, parallel RL also, if there is an RL. So again, that makes the circuit more general. And this is the kind of simplified, again, to show the R prime L instead of 2 or 3 resistors, and I will rename C green to CL. Just again, CL may include a load capacitance if it exists. So CL is C green plus maybe if there is a load capacitance between the output and ground, it will also be part of the CL. So that's the circuit that we have. It's not too complicated, right? I mean, a couple of resistors, 2 sources, 3 capacitors. I think we can deal with that. So R prime L may include any load resistance. CL may include the input capacitance of the next stage and or parasitic load capacitances. I called V sig, V prime sig, and R sig, R prime sig. And now, so if you notice that there's a prime here, I mean, they're equal to V sig and R sig in the case of MOSFET. And we will see for the case of BJT why they're called V prime sig and R prime sig. So there is a reason why they're now primed. But for the MOSFET case, V prime sig is just V sig. R prime sig is just R sig. So in the case of the BJT, and here's the common emitter amplifier with active load, if I do the small signal equivalent circuit with the capacitors of the transistors, I will get something like this. So kind of similar, except for R pi 1, which we did not have, and this RX1. Ignore this. We're no longer discussing this in 311. So we have R pi 1, and then everything else is almost the same as the MOSFET case. So in order to do this, the calculation once and not repeat it for the BJT, I will take this part of the circuit, so V sig, R sig, and R pi 1, and replace it by its Thevenin equivalent. So this is like V Thevenin for the part of the circuit inside the red circle, and R Thevenin, the Thevenin resistance for the circuit inside the red circle. But I will not call them VTH and RTH. I'll call them V prime sig and R prime sig, because if I do that, and if you look at the circuit that is here below on the lower half of the slide, this is the exact same circuit as the common source amplifier, right? So if I do the common source and replace CGD by C mu, CGS by C pi, GMVGS by GMV pi 1, R prime L, CL, and consider this to be the Thevenin equivalent of this, then I get, for the common emitter case, I get the same thing as the common source case. So what I'm trying to do is not to repeat the analysis for common emitter, to just do the analysis for common source and then generalize the results for common emitter from common source. Okay, so the two circuits are pretty similar. So let's focus on common source. Here's the circuit. And remember, we're starting from the circuit, and what are we after? We are after the transfer function. We want to find the transfer function. So we want to find the transfer function of this circuit. And to do that, I would have to do a circuit analysis in order to find VO over V prime sig. Okay, so the capacitors become impedances. CGS becomes 1 over SCGS, or admittances, or an admittance Y equals SC. So we'll write some equations for this circuit. The current in R prime L is VO over R prime L, because the voltage across R prime L is VO. The current in CL is SCL times VO, because SCL is the admittance corresponding to CL. The current in CGD would be SCGD times the voltage across CGD, which is VGS minus VO. And now with these currents, I can write a KCL at the drain. The current in CGD is equal to the sum of the currents in the controlled source GMVGS in R prime L and in CL. Okay, so this is the first equation. Another equation we can write, we can do a KVL at the input. So V prime sig minus R prime sig II minus VGS equals 0. We need one more equation, and this can be a KCL at the gate, at the input. And we know that the current in CGS is SCGS VGS. So the KCL at the gate would give me that II is SCGS VGS plus SCGD VGS minus VO. Okay, now I will have to combine these to come up with the transfer function. So after a few steps of combining things, replacing things, dividing, simplifying, we get finally the transfer function. VO over V prime sig is this thing, this expression, minus GM R prime L into 1 minus SCGD over GM divided by, I don't need to read it. That's it. This is the transfer function. So now you may look at this and say, what is this? We want the transfer function to find the zeros and the poles and find hopefully like a dominant one and be done with this. But to get something like this, what can we do with this? After absorbing the first shock, and you look carefully, it's really, it's not that bad really. Now look at this. This is, it's like a 1 plus S over omega Z, omega Z1. There's only one zero. Okay, and I can tell that omega Z1 is corresponds to this minus GM over CGD. So there is only one zero. And it is minus GM over CGD. Okay, and this may be AM, but I'll verify later. The challenge is to simplify this expression in the denominator. But even that is actually just a 1 plus a quantity, all of this, times S. I will call this B1. So B1 times S, plus another quantity times S squared, and I will call this B2. So this indeed is AM, the low frequency gain, because I have 1 plus B1S plus B2S squared, and I have 1 plus S over omega Z. So if S goes to 0, this becomes 1, and this becomes 1, and the gain becomes AM. And therefore, AM must be the low frequency gain, and it's minus GMR prime. So this is the low frequency gain. And this is the zero frequency. We already derived that. And now this is just the 1 plus B1S plus B2S squared. Even though B1 is the expression for B1 and B2 are contain resistors and capacitors, and they're maybe complicated, but just a number. And if I have 1 plus B1S plus B2S squared, I can factorize into 1 plus S over omega P1 into 1 plus S over omega P2. So when you look at this, you say, oh, all right. It's just a transfer function with 1, 0, and 2 poles. It's not too bad. Basito. And we will see next how we can find the bandwidth now and any other quantities that we may need from this transfer function.